Good afternoon, everyone, and welcome to our third class of signal processing. Today, we're going to look into Laplace Transform Part 2. So, last week we looked at the mathematical principle of Laplace Transform, and we have also looked at how we can implement it to analyze circuits. Today, we're going to look into second order systems in Laplace Transform. So, last week, all the circuits that we've looked at were actually considered first order, and I'll show you now how can we differentiate or identify a second order system. We're going to see how we can evaluate the impedance of such a system or such a circuit, and how we can find the Laplace transform, which is basically the transfer function of a system, and how we can classify them based on their equation and based on how they will perform. So we're going to look into performance indicators, and we're going to learn all of this through example. As usual, if you have any question, feel free to stop me and ask me as we proceed. So let us start with the generalized impedance of a second order system. Now, when I say generalized impedance, I mean the total impedance that the circuit demonstrates at the input terminal. So if you look at this circuit here, we have three values or three components connected in series. We have a resistor R, we have a capacitor L, and we have an capacitor C and an inductor L. So we know that the impedance of the resistor is called ZR, the impedance of the inductor is called ZL, and the impedance of the capacitor is called ZC. So these are the impedances. And if I want to find the generalized impedance of the circuit, I want to see what is the total impedance as seen at the input terminal, given that V1 is your input. So if you look at this circuit, they are connected in series. And when we're dealing with generalized impedance of a circuit using Laplace transform, all you have to do is just treat it as if it's a resistive circuit and apply the rule of a resistive circuit. So if you have three resistors in series, the total resistance will be their addition. And similarly, if we have three impedances in series, then Z total of this circuit will be the addition of ZR plus ZC plus ZL, which is the total impedance of, or the generalized impedance of the circuit. However, we already established from last week that ZR is equal to R, ZL is equal to LS, and ZC is equal to 1 over SC. So all we have to do now is just substitute these values. So it becomes R plus LS plus 1 over CS. And just to maintain a standardized version, we have to just restructure it into a single fraction rather than three different terms. So all I have to do is just unify with a common denominator CS, which means I'll multiply R by CS, so it becomes RCS plus LCS squared plus 1. And just rearrange it so it will be ordered by the highest order of S, so it becomes LCS squared plus RCS plus 1 all divided by CS. And this will be the generalized impedance. So this is how we evaluate the generalized impedance of a circuit using Laplace transform. It quite simplifies the process because we don't have to worry about the frequency dependency of the impedance of the inductor or the capacitor. All we have to do is just treat it like a regular resistive circuit. So up till this point, are we clear? Do you have a question? Okay. So moving on to a different example. Let's say that I have this circuit and I want to find the generalized impedance of the circuit. So the generalized impedance is the impedance as seen in the input terminals. And usually the rule is we start from the farthest end from the input, or from where we're trying to evaluate the generalized impedance, and work our way inwards. So start from there. So if you look here, you'll notice that these two are connected parallelly. So this is parallel. R2 is parallel to C. And so if I want to find the total impedance, it's basically Z total is equal to ZR1, which is connected in series to ZL, so plus, which is connected in series to the parallel branch ZR2 parallel to C. So this is my total impedance. And all I have to do is now evaluate what this total impedance is like. So just to add a space, we'll just add a simple space here. Just to evaluate this total impedance. So if you look here, we still have the Z total is equal to ZR1 plus ZL plus ZR2 parallel with C. So this is our main formula. All I have to do is now evaluate what is ZR2 parallel to C. So we will treat it just like we treat any other resistive circuit. We'll say that a parallel branch of two impedances is basically their multiplication, so ZR2 multiplied by ZC divided by their addition, ZR2 plus ZC. And we know that because 1 over Z parallel is equal to 1 over Z1 plus 1 over Z2, which is equal to Z1 plus Z2 divided by Z1 times Z2 if I unify the denominator, which will give me that Z parallel is equal to this. So this is just as if we're treating a regular parallel resistive circuit with two parallel branches. Now all we have to do is just substitute for the values that we know of for ZR, ZC, and ZL. So we know that ZR is equal to R, so ZR2 is R2 times ZC is 1 over CS divided by let me rewrite it. So it is equal to R2 times 1 over CS divided by R2 plus 1 over CS. So now I just have to restructure it by saying, well, R2 multiplied by 1 over CS is R2 over CS, all divided by R2 plus 1 over CS. I will unify the denominator here, so the common denominator I'll have is CS, and it will be C SCR2 plus these two will counter each other out, and we can say that ZR2 parallel to C is equal to R2 over SCR2 plus 1. I'm going to call this equation 2, and I'm going to go and substitute 2 in 1. So this is what I'll do next. Substitute 2 in 1, which will tell us that Z total is equal to ZR1, which is R1, plus ZL, which is SL, plus ZR2 parallel to C, which is R2 parallel to SC, R2 plus 1. Now this is the total impedance, but we need to write it as a single fraction. So what we'll do next is unify the denominators. So if you unify the denominators, you'll end up with SC R2 plus 1, and then R1 multiplied by SC R2 plus 1 plus SL SC R2 plus 1 plus R2. Yes, Suleiman, there is a raised hand. What is your question?
Yes, Miss, about the SCR2, can
Mm-hmm.
it be rewritten as R2CS or?
Yes, it doesn't matter because A multiplied
Okay,
by B is equal to B multiplied by A, right?
okay.
So it will become this. Let's see. So this is also equal to R2 C. It's the exact same thing. So this term and this term are the exact same thing. Okay. So now that we've reached here, the next step is to expand these. So when you expand them, what do you end up with? we will have Z total is equal to R2, R1 multiplied by SCR2, it becomes SC R1 R2 plus R1 plus SL times SCR2 becomes S squared LCR2 plus SL. And then finally we have R. All of this is divided by 1 plus SCR2. Up till this point, are we clear? And then we have to do one more step just to simplify it, which is combine like terms. So for example, here we have SCR1, R2, and here we have SL. Both have the same S, right? And I'm gonna write the term with the power 2 first, and then here I have R1 and R2. So I'm just gonna rewrite it as a quadratic expression, starting with the highest power of S. So I'll start with this term, S squared LCR2 plus S as a common factor from these two, and then what do I have left? I have C R1 R2 plus L. Finally, I have the constants, which are R1 plus R2. Let's rewrite them. I give myself some space for proper writing. So we have S squared LCR2 plus S times CR1 R2 plus L. Finally, we have the constants, which are R1 plus R2, all divided by 1 plus SCR2. So this here is your total impedance of the circuit. Now, if you look at the numerator, what is the highest power of S? 2, right? S has the highest power of 2. Therefore, we call this a second order circuit or second order system because the highest power of S is 2. So the impedance for that system will be of power 2. So that's why we call it a second order system.
S refers to
Huh?
S refers to what?
S is your frequency, your complex frequency. So S is equal to J omega. It's the Laplace factor. Okay? And in general, these are the three rules that we've used to establish this. That Z, let's write them here, ZR is equal to R, ZL is equal to SL, ZC is equal to 1 over S. So we use these three rules and then we treated the circuit as if it's a regular resistive circuit. Any questions so far? Okay. So now let's move on to the concept of the transfer function of a second order system. Last week we discussed the concept, or the week before it, we discussed that the transfer function is basically what? We said that for any system, we have an input and we have an output. And in between, we have some sort of a gain. And we established that this gain is basically the output divided by the input, right? We call this the transfer function. The ratio of the output to the input is called the transfer function. Okay? So for example, for this particular circuit, in order to evaluate the transfer function, you obviously need to know what is the output and what is the input. So here you're told that the output is V2 and the input is V1. So the transfer function, and we'll call it H of S, will be equal to V2 of S divided by V1 of S. So if you want to determine the transfer function, you just have to find the relationship of v2 divided by v1. What is it equal to? And that will be your transfer function Laplace domain. So let's add some space. And evaluate it real quick. Okay, so if you look at the circuit, we are going to use the voltage divider rule. And just a quick reminder of what is the voltage divider rule. It's a rule that says that the voltage across an element that is part of a series combination is equal to V2 is equal to the impedance of the element divided by the total impedance multiplied by the input voltage. Where does that come from? From the fact that this current is exactly the current passing through the capacitor. And that current is equal to the voltage divided by the total, right? Using Ohm's law. And the current passing through the capacitor is equal to the voltage across the capacitor divided by the capacitor's impedance. So since these two are equal to each other, let me just do this. These two are equal, we can do cross multiplication and establish that V2 over V1 is Z over Z total. Okay? So now we already know what is the relationship between the output and the input. V2 over V1 is equal to ZC over Z total. So all we have to do now is evaluate what is ZC over Z total equal to. So this is our original formula. We know that ZC is equal to 1 over CS. This is from the rules, from the Laplace transform rules. So I call that equation 2. Next thing is we need to find what is Z total equal to. We've already solved it in the previous example, example 1, but I'll redo it one more time just to ensure that it's clear for everyone. Z total is the total impedance of the circuit. Since all elements are connected in series, we will treat it as if it's a series resistive circuit. So it will be ZR plus ZL plus ZC, which is equal to R plus LS plus 1 over SC. All I have to do is now unify this denominator so that I can have a singular term for ZT, a single fraction, which the common denominator will be SC. So it will be SCR plus S squared CL plus 1, right? And I'll rearrange it just so that I can have the first power to be the highest power of S, plus SCR plus 1 over SC, and that would be my Z total. And I'm going to call that equation number 3. And then I'm going to substitute 2 and 3 in 1. So we can say that V2 over V1 is equal to ZC, which is 1 over SC, divided by Z total, which is S squared LC plus SCR plus 1 all over SC, right? Now just to circle back to that question, SLC is equal to SCR. Just to keep it consistent, SC. Now you'll notice that both numerator and denominator have the same numerator, so these cancel each other out. And what we have left is V2 over V1 is equal to 1 divided by S squared CL plus SCR plus. This over here is your transfer function. Okay? So the transfer function is the output divided by the input. We've already established the transfer function. However, there's something called the standard form. So what is the standard form of a transfer function? Is when the denominator, so it is something divided by something. We already established that the transfer function will always be a fraction because it's an output divided by the input. But the standard form is when the denominator is in the form of s squared plus a term multiplied by s plus a constant. So s squared factor has to be 1, not CL. It has to be a singular value. So just to restructure it in the standard form, I'm going to take CL out as a common factor and divide each and every term by CL. So I haven't changed that value of the equation. It still remains the same, right? But what does this do is that your transfer function becomes V2, where V1 is equal to, so 1 over CL, this CL over here, 1 over CL, divided by, these two cancel each other out, so S squared plus the C and C cancel each other out, so it becomes SR over L plus 1 over CL. And this is your transfer function in its standard form. Clear? So why do we put it in the standard form? This leads us to the next bit of this lecture, that the standard form tells you about the performance of your circuit. So we do have this equation here. At the denominator, this quadratic expression has a name. It's called the characteristic equation. And the standard form of a transfer function h of s is k omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So what does that mean? Now by comparison, can we compare this equation with this equation? Can be easily compared, right? And we can see that I can compare this omega n by this term, which will tell me that omega n squared is equivalent to 1 over CL, which means that omega n is equal to 1 over square root CL, right?
And the factor of
And then we can compare the factor of S. So because 2 zeta omega n is equal to R over L, then zeta is equal to R over L to omega n, right? And I already established the value for omega n here, right? So we can say that zeta is equal to R over L times 2 times 1 over square root CL, right? Which is equal to multiplying by square root CL, right? Which is equal to R over 2 square root C over L, correct? So we've already established the value for omega. Let me highlight it here. This is omega n, and this is zeta.
so
Yes.
the delta
What happened to L?
here.
Sure. Are we clear up to this point? Square root CL. So square root CL is C power half L power half, right? So L power half divided by L is what? L power minus half, which is 1 over. So it becomes R C power half divided by 2 L power half, right? So zeta is equal to R over 2 square root C over L. Make sense? So if you notice, what is omega n and what is zeta? Now that should be the logical question. You gave us this characteristic equation, you gave us the standard form, and then you just started calculating what is omega n, what is zeta. These are performance metrics. Omega n is basically the natural frequency. So let me just jump to the comparison here. Omega n represents the natural frequency, which is basically the frequency that the circuit wants to operate on, tends to operate on. Remember, we said that circuits with capacitors and inductors operate and have different performance or different resistance values based on the frequency. So we operate these circuits in frequency, and we mentioned that throughout the semester we're talking about linear circuits which operate in a singular frequency. Omega n is the natural frequency, which is the frequency that the circuit tends to operate on. Zeta is called the damping factor. And what does damping factor mean? Remember last week we talked about natural responses and forced response? And we said that the circuit will have an initial transient behavior and then it will stabilize. And recall that this initial transient is a result of natural response because it depends on the circuit, on its structure, and on its topology. Now, how does this initial transient stage looks like depends on the value of zeta. So we have these different options. The circuit could be overdamped. What does that mean? It means that it will start with an overshoot. So if 0 is your steady state value, this is your steady value. You'll start with an overshoot with a higher value, then you'll gradually decrease until you get your final steady state value. And we call this overdamped system, for example, the green line. We have what we call the critically damped system. And a critically damped system will start with an overshoot, but it will stabilize a little bit faster than the overdamped system. So if you compare, the red line reached to the steady state before the green line, right? So it's stable, we call that a critically damped system. And then we have the blue line, which is called the underdamped system, which starts with an overshoot, fluctuates between negative and positive values, ping-pongs a little bit, and then stabilizes, like the blue line. So this different type of behavior is dictated by the value of zeta,
The, the third is,
the blue line.
yeah, the blue line. When it goes lower than zero, it means like turning off.
No, it means negative. It will go positive, negative, positive, negative, positive, negative, but the amplitude will reduce until it becomes stable. It will ripple.
I'm like comparing with the example like before.
No, it will not go below zero. It will go to, you'll notice that in the, what is it called? Not the speed, but in the other meter, the tachometer, the one that goes from 1 to,
Ah,
you notice
yeah.
ripples? These are the ripples. Does that make sense? So how does that depend on the value of zeta? It's a simple rule. If zeta is greater than 1, based on your equation, remember that we compare the transfer function to the standard form. Calculate the value of zeta. If zeta is greater than 1, you're going to have an overdamped system. So if zeta is greater than 1, it will go like this. In that case, this means zeta greater than 1. If zeta is equal to 1, you'll have a critically damped system. It will drop a little bit faster to the stable value. So in this case, zeta is equal to 1. If zeta is a fraction between 0 and 1, 0.4, 0.2, it will start to ripple. But the ripple will change. How fast or how slow it will add up. If zeta is equal to 0, we have an undamped system. What is an undamped? Damping means تثبيط, يعني to stabilize, to lower from that overshoot until it gets you. So if it's undamped completely, that means it will never stabilize. It will continuously fluctuate up and down with a steady value. It will not decrease. Sometimes you want the system to behave like this. For example, if you want to design a clock or you want to design a train of pulses, something that will continuously produce an output. You don't want it to have a stable line. And finally, we have what we call an unstable oscillation, and that is if your zeta is a negative value. So an unstable oscillation means it will continuously increase. It's not decreasing to a stable value, it's actually increasing. So we call that an unstable oscillation, and usually we want to avoid that.
So it becomes wider.
It becomes larger. The oscillation goes larger by the time, and usually we want to avoid that type of oscillation. So this is how zeta is considered a performance metric because it tells you how the system will reach its steady state. Is it going to immediately reach it? Is it going to gradually reach it? Is it going to fluctuate a little bit and then reach it, and so on?
For the under comes to the zero, you said we wanted
Sometimes, yes, you want to design an undamped system. You want it to continuously fluctuate.
It's like the devices using output.
Oh no, that's the heart reading. But what you want, for example, you want to create a clock, a digital clock. So when you want to create a digital clock, basically you want to have something that fluctuates. For example, every transition from high to low is a second. So you want to have continuous transitions, high, low, high, low, high, low, because you want to create that digital clock. So that is, you want it to behave like this, right? So you don't want it to be damped. You don't want it to reduce. You want it to continuously. So that's an example of an undamped system. Does that make sense? So now, just going back to the transfer function, to the Laplace transfer function, and let's go here. You can see we have two performance metrics. We have the natural frequency. What is the frequency that the circuit will operate on? And we have the damping ratio. You can use this in two different ways. Way one, if you have a circuit and you want to judge its performance, so you will calculate omega n and zeta based on the values of components that you have. Or if you are the designer and you're told design a circuit that does this, then based on that, you know what value of zeta I want, what value of omega n I want, then I'll calculate the component values that will give me the desired zeta or the desired omega n. Does that make sense? Another performance metric, so I'm just gonna list them here. From this equation, we can evaluate omega n, which is the natural, undamped natural frequency, and we have zeta, which is the damping factor. We can also evaluate tau, which is equal to 1 over omega n zeta. And tau is the time constant. And we already established last week that the settling time, the time where we assume that we've reached the steady state, is equal to 5 tau, which is 5 over omega n zeta. So we can find tau, we can find the settling time, we can have the natural, undamped natural frequency, we can find the damping factor, all by just looking at the transfer function, right? Additionally, if you evaluate the unit step response, so if you have a system and you have an input and you have an output, if your input is a unit step, your output tells you a lot about the system. So sometimes you design a system and to test it, you subject it to an input that is a unit step just to see how the output will react. And this is an example of a unit step response where the input was a unit step, simple line from 0 to 1, 0 to 1. And this is your output. It starts with an overshoot, fluctuates and stabilizes. So you can tell that this system is underdamped, right? And based on this unit step response, there are other performance metrics that we can evaluate. Specifically, we have the overshoot, which is a percentage, which is how high it will exceed the steady state value. So for example, let's say the steady state value is A. It should stabilize at a value of A, but it overshooted to a value of B. So that means the overshoot percentage is equal to B minus A over A percent. And the time it takes to get to 0.9 or 90% of your steady state value is called the rise time. When you get to 90% of your final value, it's called the rise time. And the time that you want to get to the overshoot is called the peak time, how long it will take before you get to that peak. Now, why are these performance metrics? The overshoot is very important because let's say you've designed a full system. Some parts of this system are sensitive. For example, you have a diode or transistor where there is a breakdown voltage. If you exceed that value, the component will burn. So you want to know the overshoot so you can avoid that your overshoot might break down your components. So it's very important to understand or evaluate what is the value of the overshoot. Or what is the percentage of overshoot? Because if you apply 1 volt and you have 20% overshoot, that means if you apply 4 volts, the 20% of a 4 volt is different than 20% of a 1 volt, right? So you need to know what is the maximum limits of your input. And that's why when you see electronic devices, there is a lot of operating conditions that the input should not exceed this much, and this is based on that evaluation. In addition, The rise time tells you how long it takes the system to boot and reach 90% of its consumption. If there are some examples for capacitors that might need to charge. So this rise time tells you how fast or late the system will respond to an input, because you apply input at 0 seconds, but you only get to 90% of output after T rise, after some time. So this gives you the performance delay of the system. And sometimes this is very important. How long will take a car to go from 0 to 60, right? How long it will take your heart pace monitor to respond to a change in your pace. Makes sense? Acceleration or 0 to 60 is actually a mechanical rise time. We're focused on electrical rise time. So for example, let's say a heart monitor. How long will it take from the time that your heart rate changes until you can see it on the screen? It's very important, right? So this is rise time. Peak time, when at which given point of time am I reaching that overshoot? So when am I expecting my system to be overloaded with power? Make sense? And finally, we have the settling time, and we already established that settling time is 5 tau, and we can get from the equation. So far I've given you a list of performance indicators. We have omega n, we have zeta, we have damping time, damping frequency, we have tau, we have settling time, we have T rise, we have percentage of overshoot, and we have T peak. Now, these are from the formula, from the equation, from the transfer function, and these are from the unit step response graph. So some performance metrics can be easily evaluated from the transfer function, and some of them require that you perform a test, you evaluate what is your unit step, plot it, and then from the graph evaluate them. Does that make sense? So these are the performance metric. I think I explained omega n, zeta, tau, and ts, but not omega d. Omega t is also follows an equation. It depends on the value of omega n and zeta, and this is tau, and this is omega d. Okay, omega d is the damped natural frequency. So omega n is undamped without the damping factor. Omega d is if you apply damping factor, what will be the damped natural frequency. Now with that, let's have a quick example. Let's look at the circuit diagram. It's the same circuit that we had earlier, the series RLC. And this can give you a hint of what to expect during exam questions. It will not be just evaluate one thing. It will be determine for V2, A, the static voltage, B, the percentage overshoot, C, the rise time, peak time, and settling time. So you're given a circuit, you're given values for components, you're given the input value, you're told that the output is V2, and then you're told to find all of these values. So let's start with the first expression, the static voltage, but first let me copy the circuit and the values just to give myself some working space. So okay, so this is the circuit. These are the values of component we are given, and this is the transfer function, which we have already established. Just a moment, not this one, it is this one. Just a moment. This is the transfer function that we've calculated earlier in the example, right? Now we have values of components, and first thing we need to know is the static voltage. Based on the question here says, first thing, evaluate static voltage. So what does static voltage means? Static means the steady state voltage after the ripples, after the initial transient state. What is the final static يعني الثابتة value? So to evaluate the static voltage, I went back to the circuit, and this is my transfer function. So basically, we need to know what is V2. From this bit, we can establish that V2 is equal to H of S times V1 of S, right? Let's look at what is the value of H of S. This is the transfer function. I'm going to just substitute R equals 2, L equals 1, and C equals 0.16. So H of S is equal to 1 over 1 times L is 1, C is 0.16, divided by S squared plus R over L, 2 over 1, S plus 1 over 1 times 0.16, which is equal to 0 point. Now, some extra space here, which is equal to H of S is equal to 0 point or 6.25, which is 1 over 1 times 0.16, divided by S squared plus 2S plus 6.2. So we just substituted, that's step one. We ended up with the transfer function. Let's substitute this here, but we don't have V2 of S. We have V2 of T, right? We're told that it's equal to, we don't have V1 of S, we have V1 of T. We're told that V1 of T is equal to 2. So we're going to use Laplace tables to find V1 of S, which will be equal to 2 over S. Okay? Taking these into consideration, so I'll call this equation 1, 2, 3. I'm going to substitute 2 and 3 in 1, which will tell me that V2 of S is equal to 6.25 divided by S squared plus 2S plus 6.25 multiplied by 2 over S, right? However, this will give me V2 of S. The question is, what is the final value of V2 of T? But not just V2 of T, final value of V2 of T. So it doesn't mean that I will just use the inverse transform to find V2 of T. I need to find the final value, which is when T is equal to infinity. So for that, I'm going to invoke one of the theories that I've studied. So instead of having to go do partial fractions, manipulations, try to solve for inverse transform to make it match the table, remember we said theorems have the purpose of simplification of math, of calculation. So all I have to do is just use final value theorem, which states that the limit of v of t when t is equal to infinity is equal to the limit of v of s times s when s is equal to 0. So I need to find v of t when t is infinity. That's what I need to know, the final value. So I'll just substitute in the right hand side of the equation. I already know what is v of s. V of s is 6.25 times 2 divided by s squared plus 2s plus 6.25 times s multiplied by s, because it's sv of s, and let s equal 0. This s and this s cancel each other out. Any term that have s on it is a 0. What do I have left? 6.25 times 2 divided by 6.25. 6.25, 6.25 cancel each other out. So it's equal to 2. Make sense? Let's retract. start from the beginning. So up till this point, are we good?
B, limit of B t.
So this S came from here, from the equation. This S and this S counter each other out. Yes? And it says the limit when S is 0. So I'm going to substitute every term with S on it as S is 0, which means the term with S squared is 0. The term with 2S is 0. So what do I have left?
And
6.25 times 2 divided by 6.2, which is equal to 2. So the static voltage is equal to 2. The limit when V of t when t is equal to infinity is 2. That's it. So this is much, much simpler than if we had to go through the inverse transform and then replace t with infinity, right? This is a way much simpler. If you do that, you will still get 2, but it will be after a lengthy calculation. Make sense? So that's when I say, please learn how to utilize the theorems to make it easier for you to calculate math, and it will save you time on the final exam as well. Okay? So that covers the first question, which is evaluate the static voltage. And we said that the static voltage is equal to, and then it's asked to find the percentage overshoot that rise time peak time. However, we're given this graph to help us with things that require graph. But if you look at the graph, we have multiple outputs, right? It depends on the topology, it depends on the value of zeta. So we have to first know which zeta are we working with. So based on that, we can tell which curve we should use. So back to the equation. To find the percentage overshoot, I have to tell which curve I'm using so that I can calculate the percentage overshoot, right? And to calculate which curve I'm using, I need to find the value of zeta. And to find the value of zeta, I need to compare my transfer function here with the standardized form, right? So I'm going to write the standardized form and then do the comparison. So the standard form is your transfer function is equal to omega n squared times a constant k divided by s squared plus 2 zeta omega n s plus omega n squared, right? So I'm going to compare the standard form with equation 2 in order to identify the value of omega n and the value of zeta. By comparison, and then I'm going to focus on the characteristic equation. So I'm going to compare third term to third term. Omega n squared is equal to 6.25, which means that omega n is equal to what? The square root of 6.25, which is equal to 2.5. And what is the unit for omega? Radians per second. Then, based on that, I can move on to the next step, which is the middle term, 2s. So 2 is equal to 2 zeta omega n, right? Which means that zeta is equal to 2 divided by 2 omega n. And I already evaluated omega n to be 2.5, so zeta would be equal to 1 over 2.5, which means that zeta is equal to 0.4. So we've established the value of omega n, we've established the value of zeta, which means now I know which curve I need to use, which is the curve where zeta is equal to 0.4, the red one. Clear? So now I know which zeta is. I can calculate the percentage overshoot because this is the unit step response. When the input is 1, this is the highest peak value, which is here, right? So let's calculate it, but I want you to pay attention to one small detail. If you look at the scale is not decimal. It's not 10 points to each measure point. Just a moment. So you'll notice that how many steps we have? 1, 2, 3, 4, 5, 6, 7, 8. It's an octave scale, not a decimal scale. Notice we have 1, 2, 3, 4, 5, 6, 7, 8, right? And then if I want to measure this, I have 8 and then 1 and 2, right? So it's basically 1 plus 2 over 8, right? 2/8. So the A value is 1, the B value is 1 and 2/8, right? So that means my percentage overshoot is equal to 1 and 2/8 minus 1 divided by 1, which is equal to 2 over 8. 2 over 8 is how much? It's 1/4, right? Which is in percentage, it's 25%. Make sense? So
But
now,
how to write it? Like one, two,
1 and 2/8.
1, 2. So
You
I
can
have to
either write
calculate.
it as this or write it as 10 over 8. Because 1 is 8 over 8 plus 2 over 8, right? So it's 10 over 8 minus 8 over 8 divided by 8 over 8, which is 1.
I mean, like I have to calculate.
Yes, you have to calculate it because so I measured it. I calculated. I have 1 and then 2 units out of 8 to the next, right? 1 and 2/8.
So below I have to calculate another one. Then above the one will be.
Above the 1, you'll start to add. Make sense? Is it clear?
Yeah.
So now we've evaluated the percentage overshoot, that it's 25%, right? Next thing they want is the rise time. And the rise time is the time that it takes to get to 90% of your full steady state value. And here we are looking at the unit step response. So to get to 90%, we want to get to 0.9, right? So I have to go and look at where does 0.9 almost fall. So this is where 1 falls. Let me scale it down. This is where 0.5 is, right? This here is 0.75, right? Approximately it's here. Approximately, okay? So this is where 0.9, so I'm gonna find where is the intersection point of 0.9 with my graph of zeta equals 0.4. And then I'm gonna see where is that in the x-axis. Make sense? I want you to pay attention to the x-axis because x-axis is omega n t. It's not just time, it's omega n times time, right? And then again, if you look at it, it's an octave scale. So I have 1, 2, 3, 4, 5, 6, 7, 8 units. And 8 full units are equal to pi. So 1 unit is 1 over 8 pi. Make sense? So if I zoom in, how many units do I have? 1, 2, 3, 4 and a half, right? So omega n times t rise, because it's omega n times t, is equal to what? 4.5 eighths pi. Make sense? And therefore t rise is equal to 4.5 over 8 times pi divided by omega n, right? And I've calculated omega n. In order to calculate zeta, we had to first calculate omega n, which was 2.5. So t rise is 4.5 over 8 times pi over 2.5. And then we can calculate it. So what would that be equal to? We can have a quick calculation. Let me see. It would be equal to 0 point, my pen. So t rise is equal to 0.71 seconds. Make sense?
Yes.
So now we can say that t rise 0.71 seconds. Then I need to find t peak. I've already established that this is the peak value. Now I have to see where does it intersect with the axis. So let's calculate. We have pi and 1 out of 8, right? So we have one full scale pi, full pi, and then 1 over 8. So this is basically 8 over 8 pi plus 1 over 8 pi, right? So 9 over 8 pi is equal to omega n t peak. Make sense? Where did the 9 come from?
Yeah.
So up till this point, you have 8 over 8 pi. And then we have this one more, plus 1 over 8 pi, which is 9 over 8 pi, right? Or in other words, 1 and 1/8. Which means that I just wrote it this way because it's easier to use in the calculator later on. So therefore, T peak is equal to 9 over 8 pi over omega n. We've already established omega n is 2.5, which is equal to, then we can go ahead and use the calculator, which will give us a value of, let's check, 1.42 seconds. So this is, let's go back, T peak is equal to 1 over 4 seconds. The interruption. Okay, so now we have, where am I at? Now we have T peak, which was 1 over, which was 1.42. We have T rise. What is the last thing we have to evaluate? T settling. However, T settling is slightly different because we don't calculate it from the graph. We said that T settling is equal to 5 tau. So we can calculate it as T settling is equal to 5 tau. Tau is equal to 1 over omega n zeta, which is 1 over 2.5 times 0.4, which is equal to 2.5 times 0.4 is 1. So Ts is equal to 5 seconds, which we can write here. So Ts So just by looking at the circuit, if you're given the circuit and told evaluate its performance, you can say, well, based on the values of components I'm given, I know that it will take it 0.7 seconds to get to 90% of its final value. I know that it will hit a peak at 1.4 seconds. I know that this peak will be 25% more than the input value. I know that it will stabilize at 2 volts if your input is 2 volts. And I know that it will tend to operate at a frequency of 2.5 radians per second. And I know that it is, now, if zeta is 0.4, you know that it is overdamped, underdamped, or critically damped. It is underdamped. It will fluctuate. It will go high, low, high, and until it's finally, after 5 taus or after 1.42 seconds, after 5 seconds, it will be stable at 2 volts. Make sense? So we just, by looking at it, you can tell how it will behave.
Just by looking, aren't all the signals, the waves are under?
Is the black one underdamped? If you look at the two peak values, both values are hitting the same peak value of 2 volts, right? If you look at the purple one, which is equal to 1, you'll see that it reached faster than any other curve to the steady state, right? If you look at the blue one, you'll notice that it's not fluctuating positive or negative, but it's gradually making its way to become stable. Make sense? And all of this depend on what? On zeta. And what does zeta depend on when we calculated it? It depended on this term, 2s. And where did this term come from? The value of L and R, right? So if L and R changed, things will change. Even for the same circuit, if the value of R and L change, everything will change. Make sense? So that means if you look at the circuit structure, if you look at its value of components, you can do simple calculation and tell you everything about its performance. It could be used either to judge the performance of, let's say you have two circuits and you want to compare their performance, or if you are a designer and you're tasked to design something, then you'll say, well, I want zeta to be 0.7, so I'm going to use values of R and L that will give me this 0.7. Make sense?
Yeah. For more advanced, this can be done automatically, just giving the inputs. So if the values.
You will do that as part of your group project. You'll do the calculation, okay? So I will highlight this later, but you need to look at it at this perspective. How will it behave? And this, especially this delay is very important because it tells you how fast or how long it takes or how much accurate it is. Because if you look at this factor, it's not just time, it's frequency, right? So also it tells you how accurate you are in terms of frequency. We'll discuss roll-off later on, but up till this point, is it clear? So just to highlight what we've covered today, we looked at the second order systems. We established that a second order system will have a second order overall impedance, and it will also have a second order characteristic equation, which is the equation in the denominator of the transfer function. We established how we can find the transfer function, how we can compare it to the standard form, how we can use it to evaluate performance metrics, including natural frequency, damped natural frequency, damping factor. We talked about different classification of damping factors based on their values. And we talked on how we can judge or evaluate performance metrics using the characteristic equation and the unit step response. So I think this covers our answer. So if you want to practice with more problems, you can go to Erwin and Nelm's Basic Engineering Circuit Analysis. Chapter 14 has more examples. You can find this at the library, or you can go to the reading list available in the module handbook. And in there, you'll find a soft copy through your UWE credentials. Online, do we have a question before we end this session? Okay, so we'll stop here.